Buckle up, cosmic thrill seekers, as we blast off into the dazzling enigma of quasars, the brightest beacons blazing across the universe with a fury that outshines entire galaxies. Welcome to a mesmerizing journey through the heart of these celestial powerhouses, where we'll unravel their secrets, from their explosive births at the dawn of time to the mind-bending physics that fuels their unimaginable brilliance. What makes these distant monsters shine so fiercely? How do they shape the cosmos we know? And what mysteries do they still hold that could rewrite our understanding of reality? Get ready for an epic adventure packed with stellar science, groundbreaking discoveries, and cosmic wonders that will keep you glued to every word. Let's dive into the mysteries of quasars together. Picture the night sky, a vast canvas sprinkled with stars and galaxies, each a whisper of light traveling across billions of years. Now imagine a single point outshining them all, a beacon so intense it could eclipse the combined glow of 1 trillion suns in a matter of seconds. That's a quasar, short for quasi-stellar radio source, one of the most luminous and energetic phenomena in the universe. Discovered in the 1960s, quasars are the radiant hearts of distant galaxies, powered by supermassive black holes devouring matter at their cores. They emit energy across the electromagnetic spectrum, from radio waves to gamma rays, and their light has journeyed to us from the early universe, offering a window into cosmic history. But quasars aren't just bright, they're enigmas, challenging our understanding of physics, gravity, and the evolution of galaxies. As we embark on this exploration, you'll see how these blazing titans have transformed astronomy and continue to puzzle scientists today. Doesn't the sheer power of quasars make you eager to learn what fuels their fire? The story of quasars begins in the mid-20th century, a time when radio astronomy was revolutionizing our view of the cosmos. In 1960, astronomers Alan Sandage and Thomas Matthews identified a star-like object coinciding with a strong radio source called 3C48. It looked like a star but emitted radio waves far stronger than any known star, and its spectrum was bizarre. Lines shifted dramatically to the red, indicating it was receding at incredible speeds. Dutch-American astronomer Martin Schmidt cracked the code in 1963 with another source, 3C273. He recognized the redshifted lines as hydrogen's Balmer series, shifted by a factor of 0.158, meaning the object was 2 billion light-years away and moving at 47,000 kilometers per second. This wasn't a nearby star, it was something extraordinarily distant and luminous, shining with the power of hundreds of galaxies from a point-like source. Schmidt coined the term quasi-stellar object, or quasar, and the floodgates opened. By the 1970s, hundreds were catalogued, their redshifts revealing they were among the most distant objects known, light from when the universe was young. This discovery, earning Schmidt acclaim, showed quasars as relics of a more violent cosmic era. How did these puzzling points of light turn out to be the universe's brightest spectacles? At their core, quasars are active galactic nuclei, or AGN, the energetic centers of galaxies where supermassive black holes, millions to billions of times the sun's mass, gorge on surrounding matter. Picture a black hole like Sagittarius A** in our Milky Way, but scaled up and ravenous. Gas, dust, and stars spiral inward, forming an accretion disk, a swirling, flattened ring heated to millions of degrees by friction and gravity. As material falls toward the event horizon, the point of no return, it accelerates to near-light speeds, releasing tremendous energy through electromagnetic radiation and relativistic jets, beams of plasma shot out at nearly the speed of light along the black hole's magnetic field lines. These jets, extending thousands of light-years, collide with interstellar gas, producing shock waves that emit radio waves, explaining quasars' early detection as radio sources. Not all quasars are radio loud, about 90% are radio quiet, shining mainly in optical, ultraviolet, and X-rays from the disk itself. The black hole's spin, up to 99% of maximum, twists spacetime via frame dragging, amplifying the jet's power. This engine turns quasars into cosmic lighthouses, visible across billions of light-years. Isn't it astounding how a black hole's hunger creates such brilliance? Quasars come in varieties, reflecting their orientation and activity. Blazars, a subset, appear when a jet points directly at Earth, like a flashlight in your face, making them extraordinarily bright and variable, flickering in hours due to relativistic beaming, light compressed and intensified by near-light speed motion. Seyfert galaxies, milder AGN, show quasar-like spectra but in closer, spiral galaxies, divided into Type 1, broad emission lines from fast gas, and Type 2, narrow lines from slower clouds. The unified model suggests these differences stem from viewing angle, thus tori obscure the core in Type 2, while Type 1 offers a clear view. Radio galaxies, like Centaurus A, feature massive lobes from jets interacting with intergalactic medium, glowing in radio. Quasars proper are the most luminous, often in merging galaxies where gas fuels the black hole. Their evolution ties to galaxy formation. Quasars peaked 10 billion years ago, when mergers were common, now rarer as the universe quiets. This diversity shows quasars as stages in black hole growth. How do these variations paint a picture of cosmic evolution? The energy output of quasars boggles the mind. A typical quasar radiates 10 to the power of 40 watts, 100 times a galaxy's light, from a region smaller than our solar system, the accretion disk scale. The brightest, like 3C273, shine with 4 trillion suns' luminosity, visible from 3 billion light-years. This power comes from gravitational potential energy converted to radiation with 10% efficiency, far surpassing nuclear fusion's 0.7%. Eddington limit caps accretion, radiation pressure balances gravity, but quasars often exceed this via super-Eddington flows, where clumpy gas allows faster feeding. Jets carry kinetic energy, plowing through gas at 10% light speed, heating it to millions of degrees for X-rays. Quasars' spectra show broad absorption lines from outflowing winds at thousands of kilometers per second, carrying mass and regulating growth. This feedback quenches star formation, explaining why massive galaxies are red and dead, their gas heated or expelled. Quasars thus sculpt their hosts, a cosmic symbiosis. Can you fathom energy rivaling galaxies from a pinpoint? Quasars offer a time machine to the early universe. Their high redshifts, up to Z equals 7.54 for J0313-1806, light from 670 million years post-Big Bang, show them as young universe denizens, when black holes grew rapidly. This quasar epoch peaked at Z equals 10 billion years ago, aligning with galaxy merger peaks. Studying quasars reveals reionization, when first stars and quasars ionized neutral hydrogen, ending the cosmic dark ages around 150 million to 1 billion years post-Big Bang. Quasar spectra show Lyman alpha forests, absorption lines from intergalactic hydrogen, mapping this transition. The Gunn-Peterson trough, a complete absorption at high Z, confirms neutral gas pre-reionization. Quasars' light, probing billions of years, traces element distribution and galaxy evolution. How do these ancient lights illuminate cosmic dawn? Observations have evolved dramatically. Early radio surveys like the Third Cambridge Catalogue, 3C, identified quasars, but optical telescopes struggled with their point-like appearance. The Hubble Space Telescope, launched 1990, resolved host galaxies, showing quasars in merging systems, supporting fueling theories. Chandra X-ray Observatory, since 1999, captures hot gas in jets and disks, while Spitzer's infrared pierced dust. The Event Horizon Telescope's 2019 M87* image hints at quasar-like processes. Ground arrays like ALMA map molecular gas-feeding black holes. In 2023, JWST's infrared views of high-Z quasars revealed mature black holes defying growth models, suggesting direct collapse from gas clouds. These tools peel quasar layers, but mysteries linger. What sparked their rapid growth? One enduring mystery is quasar unification. Do all AGN types stem from the same phenomenon, viewed differently? The torus model proposes a dusty donut obscuring the core. Edge-on views see Type 2 Seyferts with narrow lines, face-on show Type 1 with broad lines from fast gas near the hole. Variability supports this. Some quasars change look, switching types as dust clears. But clumpier tori or wind-driven obscuration complicate it. Another puzzle, quasar lifetimes. They shine for 10 to 100 million years, but black holes grow over billions. Do they cycle on and off? Feedback self-regulates, jets expel gas, starving the hole until mergers refill. High-Z quasars, like SDSS-J0100 plus 2802 with 12 billion solar masses at C equals 6.3, challenge models. How did they bulk up so fast? Seeds from population 3 stars or direct collapse offer answers. Quasars' role in reionization, their UV light ionizing gas, remains debated. Stars might dominate. These riddles drive research, promising breakthroughs. Quasars influence cosmology. As standard candles, their luminosity varies, but X-ray optical relations standardize them for distance measures, probing dark energy. Lensing by quasars maps dark matter, as in quadruply imaged quasars like the Einstein cross. Their distribution traces large-scale structure, filaments where galaxies cluster. Quasars test relativity, strong gravity near holes warps light, as in microlensing variability. Their study refines the universe's timeline, from Big Bang to today. The future gleams. JWST's 2025 to 2030 data will detail high-Z quasars, probing growth. The Rubin Observatory's Legacy Survey will map millions, tracing evolution. LISA's gravitational waves will catch mergers fueling quasars. ALMA's gas maps will reveal feeding mechanisms. Could we resolve a quasar's disk? Might a nearby burst light up? Quasars beckon, full of promise. What do quasars mean for us? These brightest objects link us to the universe's violent youth, forging elements in jets, shaping galaxies. Your atoms, born in such fires, connect to their blaze. From Schmidt's redshift to JWST's gaze, curiosity illuminates them. We're cosmic observers, peering into the light. As we near the end, let's gaze ahead. Quasars, brightest in the universe, unveil black holes, jets, and cosmic birth. New telescopes, data, and dreams will decode them. What powers their shine? How will they reshape astronomy? The universe blazes, full of wonder. What questions stir your mind? Thank you for joining me on this epic dive into the mysteries of quasars, the brightest objects in the universe. I hope your curiosity blazes. If you love this cosmic adventure, hit that like button, subscribe, and ring the bell for more journeys into the unknown. Drop your thoughts in the comments. What blows your mind about quasars? What mysteries should we explore next? Until then, keep looking up, keep wondering, and let's unravel the universe together. See you in the next video, Cosmic Thrill Seekers.